Now, when we know what happens when drug attaches to receptor, there is a next question. How we bring this chemical compound to the location of that receptor? That's what we name pharmacokinetics and related to it pharmacodynamics, similar to thermodynamics and chemical kinetics. So first, you have drug at site of administration, then it comes into blood plasma, and from blood plasma, the next is distribution into a tissue. Now, next, it can be metabolized in blood, or it can be metabolized in tissue as well. And later on, it can be eliminated from human body in urine, bile, tears, breast milk, saliva, sweat, feces, whatever. So how can we introduce drug into human body? Most common is oral way. It's quite complicated. We'll discuss it later. The simplest is intravenous injection, IV dose. It can be continuous addition or it can be one-time IV injection directly into bloodstream, no intermediate. Inside bloodstream you have systematic circulation of blood. Free drug can be bound to molecules in plasma. It can metabolize in plasma. It can distribute into tissues, and finally it can reach site of action, giving pharmacological response. Again, when we say pharmacological response, it can be positive or negative or simply poisoning of human or, well, of an animal. There are different ways of inject. You can do subcutaneous, intramuscular, transdermal, you can implant drug and so on, so on. All these you can inhale. As I will discuss these other ways later in this class. Bloodstream in turn is connected to liver metabolism with metabolized drug coming back into bloodstream later on. So that would be our main way of introduction. Now, when we put chemical compound in water, it's easy to calculate concentration. Say, if I have 1 liter of water, I put 100 milligrams of chemical compound, I have concentration of 100 milligrams per liter. But if I have a slightly more complex system, so I have charcoal that absorbs 90% of my drug, now I still have 100 milligrams, but concentration of sample is 10 times less. And this is the picture we have in human body. When we inject our drug directly in blood, it does not stay in blood. It interacts with tissues, interacts with molecules in blood, so the picture is more complex. To start with, volume of your blood plasma is not too large. It's between 3 and 5 liters of aqueous solution. Now, much larger volume is so-called extracellular fluid, which is 15 liters. And to get into extracellular fluid, drug need to cross capillary epithelium. Next, coming to cell membranes, you are getting into 40-liter total body volume. 40, 42, slightly more, slightly less for a different human being. These water exchanges with environment. You have direct water uptake every day, 2 to 3 liters normally from food and drink. You lose 2 to 3 liters per day from with urine, perspiration, respiration, so on. So this is a variable as well. To describe this picture, we introduce volume of distribution. Volume of distribution is given for following equation. Total amount of drug in the body, so that's how much we put it, and divided by drug blood concentration. Again, if you take total amount of drug divided by volume, you'll have drug concentration. Now, the dose required to give a certain plasma concentration can be determined if volume of distribution of that drug is known. Volume of distribution is not physiological value. It is more a reflection of how drug will distribute throughout the body depending on physicochemical properties, solubility, charge, size, etc. Very often we calculate volume of distribution per weight of body. In this case, it's not volume anymore. It's obvious. If your weight is 50 kilograms, perhaps you are smaller than a person whose weight is 100 kilograms. It's obvious a twice larger person will have twice larger volume. So in this case, we are using liters per kilogram of weight of person, and numbers of volume of distribution in these units will be usually between 500 and 20 liters per kilogram. To figure out the real volume, you just multiply by weight of that. Just to look at real numbers. Diazepam, common well dissolved in water molecule, will have volume of distribution 0.222. Morphine will have a larger number. Pentobarbital even larger. Cannabinoids will have very high volume of distribution. Just to give a flavor, if person's weight is around 100 kilograms, well, it's a very big guy. You'll have a volume for cannabinoid being between 900 to 1100 liters. You see, it's not a real number. It is impossible to have a volume 900 liters in human. Even for diazepam, if you have distribution volume 2 and you are not a big person with weight of 50 kilograms, volume will be 100 liters. So distributions volumes are always much larger than real volume of the person. A very simple rule that if your distribution volume is a small number, zero point 0.1, 40% of drug is in water. Still 60% is out. If distribution volume is 1, only 4% is in water. If, like in THC, you have distribution volume of 10, a fraction of 1% of drug is in plasma and in water. Several more distribution volumes. Heparin, fantastically well soluble drug, will have relatively small distribution volume of 4. Warfarin, again very common compound, will have 8. Now, tricyclic nortriptyline will have 1200. Iodine containing compound is very hydrophobic, will stay mainly in fat tissue, will have 4600. And chloroquine, you may see this compound, it was recently falsely advertised as a cure from COVID, have fantastically high volume of distribution of 14,000. This is for human body. That's not for kilogram. That's for 70 kilograms. So again, imagine person with 14 cubic meter volume. It's impossible. So this drug sits in fat tissue. There is 4-compartment model. Again, human body is very complex, so we need to use models. 4-compartment model of drug distribution. After administration of intravenous bolus, so one-time injection, drug is delivered to various tissues by system circulation. Fraction of dose is initially highest in blood, but then blood fraction falls rapidly as drug is distributed to different tissues. So first we introduced at moment 0. So all the drug sits in the blood. Then during several minutes this fraction drops down dramatically. It's coming into vessel-rich group, so in tissue with lots of blood vessels, but after 10 minutes it's coming into muscle, and finally after some time it coming into fat-like tissue, adipose tissue. It takes hundreds of minutes, so around 2, 3, 4, 5 hours for drug to reach this kind of tissue, and that's where it will stay for a longer time. At this moment, concentration in blood is becoming much lower, or less than 10% of starting amount. Still, all the blood, all the drug is in your body. In this, that's an example. Thiopentanol concentration. That's for dog. So in plasma, starting was 25, quickly drops down to 10 in several hours. Same drop of concentration will go in liver. In liver it will be much higher. Concentration in muscle first go up and then will go down, and concentration in fat tissue will go up all the time, will continue increasing. Why? Because it's a sulfur containing compound, so it's slightly hydrophobic, wants to be in tissue. It's important to understand that apparent volume of distribution at very first moment is relatively small. You have only your blood plasma available. And then it will go up and reach its real value. So at first moment after injection, you'll have much higher concentration, even so your drug molecule will not decay. Now, even when drug is in bloodstream, it can be bound to protein. When drug B, as you can see, is completely bound to protein, it sits in the blood, cannot reach site of pharmacological action, just small fraction will reach, and can be cleared out. Drug A that is not bound to protein easily reaches the site of pharmacologic action and easily removed from your bloodstream. So that's another important parameter. We can see that different drugs are bound to protein to different extent. So in plasma, very small amount is unbound. Most of drug is bound in extracellular fluid or outside of them, or bound to protein in plasma, or bound intracellular in tissue. You do not have free molecules. Another picture showing percentage of drug unbound in plasma. For example, lithium salts, yes, 100% unbound. Antibiotics like penicillin, phenobarbital molecules are mostly unbound. At other hand, naproxen, diazepam, ibuprofen are mostly bound in plasma. Some of them are bound to 99.9% extent.